Okay, so okay, it's recording. Yes. Okay. So yesterday we were looking at some. So yesterday we saw Miller-Rabin primal tree test, and to prove it, we require some algebra. So we were looking at the prerequisites from some of the prerequisites from algebra, and we had covered groups. So today will cover rings and fields, and then we'll look at the proof of the Miller-Rabin primal tree test. Okay. So before that, do you have any questions about groups?
No, the groups are clear to me.
Yeah. Yeah. So then let's look at rings. Okay. So yeah. So okay, recall that in groups were algebraic structures where you could do one operation, right? Rings are algebraic structures where you can do two operations. So
So I have a question here that why can't we do two operations on a group even though we define one binary operation, but
right.
why can't we do? So I have two questions here that why can't we do more than one operation in a group, number one, and second, is it necessary that the operation has to be a binary operation only and cannot be a ternary or any other kind of
Okay.
operation?
So that's how a group is defined, right? It's a set with a binary operation on it, just one operation on it.
Okay, okay,
Yeah. So algebraic structures with two operations, two binary operations of them are group rings and fields.
okay.
Yeah.
And what about more than two, say three or four or n number of binary operations? Do we have algebraic structures
Mm,
for that as well?
Not that I'm aware of.
Okay, okay.
Yeah. Okay, so this is said to be a ring. If basically three things should happen, okay, four sort of. First one is that R under the first operation should be a group. Second is okay, for any A comma B in R, AB, okay, A B is in R. So the second operation must satisfy three things: uh, closure, associativity, um, okay, yeah. So I'm denoting the multiplicative identity by 1 and the additive identity by 0. A in R, so that A1 is equal to 1, A equals to A. But an inverse need not exist. And fifth, uh, the multiplication should distribute addition. Oh, sorry, this is an abelian group. Yeah. Yeah. So these are the 5 things that an algebraic structure must satisfy to be a group, to be a ring. So is this fine?
So then, I mean, instead of defining, say, 5 here, we could have easily written, say, R comma plus should be a group, should be an abelian group, and R comma dot should be a group.
No, no,
That's
no.
it.
It's not a group. So in group, you need 4 things, right? You also need inverse.
So yeah. So what is, I mean, which property of the group is missing here? Closeness is there.
Closure is
Associativity.
there, associativity is there, identity is there, inverse is missing.
Oh, inverse is missing. Okay.
Yes.
Why this inverse is so very special? I mean, where is the harm if we include inverse also in the definition of the ring?
Okay, it's this. So rings were uh, studied. So okay, rings were sort of introduced to study properties of integers, and this is not a. If you include inverse, this is not a ring. So this is for like, yeah, I think historical reasons. So when
I
you
could,
include,
I
yeah,
could not, I could not hear this properly.
okay, so rings were initially introduced to study integers. So the definition of ring was trying to capture the properties of integers.
Okay.
Yeah,
And
and
what is the harm?
integers. Okay, so integers. Yeah,
So what is the harm if I include the inverse here as well?
there is no harm. It's just not a ring.
Okay.
Yeah.
Okay. And
So okay,
why the inverse does
yeah.
not exist here in the ring, by the way?
Can you repeat that?
Why the inverse does not exist? I mean, in a ring.
Okay, so that's how rings are defined. So inverse need not exist. It can exist. It need not exist.
Oh, I see. I
Yeah.
see.
So for example, okay, we'll see fields later, and we'll see that okay, every field is a ring, and in fields the inverse do exist.
Okay. Okay.
Yeah.
Okay.
So one example is this. Another is okay. So I can okay. So this thing. Zn with addition mod n and multiplication mod n. So this is also a ring. Okay. So is this fine?
Yes. So yeah. But then I was thinking that what could be the inverse? I mean, for the first ring, jet plus and then dot. So we do have the inverse of every element, like say inverse of 2 is 1 by 2. But then 1 by 2 is not the element of the jet. Is it
Right.
so?
Yeah.
Okay.
So it's not an integer, right?
Yes, yes, yes. Right,
Yeah.
right. I understood this. So then
Yes.
what is, I mean, why to consider this distributive property and why is this relevant?
Again, so like the rings were introduced to study properties of integers and like ring and structures where you take integers and go modulo a number. So the definition of ring tries to capture the properties of things like this, structures in things like this, integers modulo n, and so on. So this is why rings were introduced. And so the definition of rings, so basically rings were defined to have everything that these things would have.
Oh, I see. So
Yeah.
can I have different operations other than plus and dot here? I mean, for the
Oh, so
ring, say.
okay, you need to okay, plus and okay, so just like yesterday, dot was just an operation, right? It need not be plus, it need not be product. So plus and product over here are two operations. You need to define. So okay, to define a ring, I need to do three things. Define a set, define plus, and define product. So for
Okay,
example, over here, the operation is not plus, right? It's plus mod n, it's product mod n. So I had to define three things: a set, an operation, and then another operation.
okay, yes, yes, understood.
Yeah,
Yeah.
right. So these are just notations, and but we use these notations because frequently, like in practice, whenever we encounter rings, it's mostly these two operations.
Yes, yes.
Yeah. Okay. So yeah. So yesterday we saw homomorphism for groups, and what were they? So they were maps that were preserving the structure, and in groups, the structure was the one induced by that one operation. So here the structure is the one induced by these two operations, right? So yeah, it's this R is set to So let's say R and S are rings. So phi from R and R to S. If for so okay, so over here I need to preserve two structures. The one induced by the first operation and the one induced by the second operation, right? So is this fine?
Yes, yes.
Yeah. And okay, I need. And again, isomorphism is similar, right? So it's a 1-1-1-2 homomorphism.
So, do we need to have, I mean, phi same in both the cases, or can I have, say, phi 1 and phi 2? Because quite possible that one mapping function may not follow both the properties.
Yeah, so then it's okay. So if a function does not follow these two properties, it's not called a homomorphism.
Okay, okay. Phi
Yeah.
should be, I mean, should be
Yeah.
same and
So
okay.
yeah, so the point of homomorphism is to capture the structure. And to do
Yes,
that, you need both the operations, right?
yes,
Yeah. So isomorphism is yeah, if it's a homomorphism. Yeah. So is this fine?
yes, yes.
Okay, so now let me introduce one thing that we would crucially use. So it's called okay. So let's say I have two rings, R1 and R2, and I want to create a new ring out of this rings, right? So direct sum of rings is one way to do it. So which is denoted by R1, R2 is this set. Okay, so it's a set of all tuples from where the first element comes from R1, the second from R2. And now I want to make this a ring. So I need to give you the addition and multiplication operations on it. And the way to do it is very simple. So R1, R2 plus let's say R1 prime, R2 prime is R1 plus R1 prime, comma, R2 plus R2 prime. And R1, R2 times R prime, again, same. Okay, so is this fine? Just the first one, the set?
Yes, it's fine, but then capital R1 and capital R2 both are
Yeah.
infinite.
So what were you asking?
So R1, it's okay, the definition wise it's fine, but then R1 and
Right.
R2 both are infinite sets.
They can be infinite sets, yes. Then this would also be an infinite set.
Oh yes, then it's fine.
Yeah. Yeah. Okay, but there is an I need to clarify something over here. So over here plus appears 3 times, right?
Yes, plus appears 3 times. Yes.
Right. So over here, okay, so over here, what does the plus mean?
So yeah, so basically whichever operation plus we have defined as a first operation of the ring, so we are individually applying it over say
No, but
whatever
so
time.
these are two different rings, right? So their plus operations might be different.
Oh yes, yes, that would be.
Yeah, so this is the plus operation of the first ring. This is the plus operation of the second ring. And this is the plus operation which I'm defining for R1 direct sum R2. So I'm
Oh,
defining, so to make R1 R2 R1 direct sum R2 a ring, and to define two operations, right? Plus and product. And what I'll do is I'll define those operations in terms of operations on R1 and operations on R2. Okay. The way I'm defining the addition operation on R1 using the addition operation for R1 and R2 in this way. And same for product. Okay. So this is the one that's being defined. This is the one in R1. This is the one in R2. Now is this fine?
yes, yes. So what is the
Yeah.
name of the symbol? You said something. This plus this XOR symbol. So what is the name of this symbol? You said something.
Oh, okay. So direct sum. Direct sum.
Okay, okay, yes, yes. Okay.
Yeah. Okay. So now, okay. So now what I'll do is I'll give you a version of the Chinese remaindering theorem, which you would end up using today. So you would have, like, if you have done some other course in complexity theory or cryptography, you might have seen, uh, an like you might have seen a version of Chinese remaindering theorem, but the one I'm going to give now is slightly different, and it's in some way a generalization of it. Okay. So
Yes.
the version we would use is this for any two distinct. Uh, so this is how you denote isomorphism. And over here, Zn, Zp, and Zq are rings. Okay, so what I'm saying over here is that a ring Zn, that is the number 0 to n minus 1 with addition modulo n, multiplication modulo n, is isomorphic to the direct sum of Zp and Zq.
So this is slightly difficult to digest. So can you take P is equal to 3 and Q is equal to 5, and then it would be easy for me to understand this.
Okay, so okay, what do you want me to do with by taking this equals to 3 and this equals 5?
So that I can see that this Zn is really isomorphic to the direct sum of the Z3 and the Z5.
Is proving that would require a lot of work. Okay, I mean it's not a lot of work, but it would take up a lot of time today. So that we don't have. Okay, so I can give you some intuitive idea of what's happening. Okay, so what this is saying is there is a 1-1 onto map between Zn and Zp, Zq. And so for every element over here, I can come up with two elements over here. So that let's say the element is A is equals A1 comma A2. I can essentially say that this is equality because of the isomorphism.
Uh, okay, okay, okay.
Okay, so
So the
basically what this lets me do is whenever I have Zn, I can replace it with Zp direct sum ZQ.
So, I mean, that is what I am interested in. Only what is the intuition behind it? So, single element is can be mapped to a tuple.
Right.
So,
Okay. So,
yeah.
so okay. At least for just this version of Chinese remaining theorem, you can just use the um, usual proof that you give.
Uh, so yeah, actually, I do not remember the formal statement of the Chinese remainder theorem, which we
Okay.
used.
So okay, the version that we might have encountered is this. Okay. What is it? So for all u comma v, where GCD of I don't need GCD because I have this. Okay. So where 1 less than or equals to u less than p, 1 less than equals to v less than p. There exists a unique x 1 to n minus 0 to n minus 1 such that x is congruent to u mod p and x is congruent to v mod p. Sorry, v mod q. So this is the version that you might have seen somewhere.
Mhm.
Yeah,
Yeah. Even though I vaguely remember, I do not remember it correctly, but probably we used to have powers, exponents over something x, something. I
exponent.
don't know.
So okay, so okay, so there is one more. Okay, so you can give a more general version of this when P and Q are need not be prime, but let's say they have it's like P to the alpha, Q to the beta. Are you talking about that?
Maybe. But then, what this Chinese remainder theorem, indicates? I mean, what's the relevance of it? I remember
Oh,
we
so
used CRT.
okay, so one. Okay, so like, are you asking for some of its applications?
Yeah, some of the use of, the this Chinese remainder theorem.
Okay, so I couldn't hear your question properly. Can you please repeat it?
Yes, there because I am using desktop today, so there could be some audio issue. Uh,
Okay.
so my voice may not be that much clear. So my question is that why do we use Chinese remainder theorem, and what could be its use? Like, say, why do we
Okay,
use it?
so we would use what? Okay, so we would see one use case today it's used to prove that the Miller-Rabin test is correct, but this is just one of the uses. It has been used at multiple places. One is to prove the correctness of RSA. Another is okay. It was even used in a version of it was even used in the AKS test.
Okay, okay, okay.
Yeah. So it's something that's widely used uh, in computer science and even and also in math. And okay, the reason is this. So let's look at the second statement that I gave you. So what does it allow me to do? I can take an element from like 0 to n minus 1 and I can replace it with two elements from P and Q, right? ZP and ZQ.
Yes, yeah.
Yeah. And
Okay.
okay, so the reason this would help us today is the following. It's because ZP and ZQ are much nicer. In fact, since P and Q are prime, in fact, ZP and ZQ are fields. We'll get to what fields are later. But so it turns out that ZP and ZQ are fields, and that's why like it's much nicer to work with them instead of Zn directly. So
Okay.
let's say I wanted to add A and B in Zn. I could sort of decompose A and B in terms of their ZQ and ZP and ZP components, quote unquote components. They are not components, but yeah. And then add them, right?
Okay. Okay.
Yeah. So I can do this for anything over Zn. So let's say I want to reason about Zn. I want to prove that something is true over Zn. I can
Mhm.
do just prove something over ZP and ZQ and then argue that this statement lets me prove it over Zn.
Oh,
Yeah, and what we'll do today is, okay, roughly what we'll do is this. I want to pick, so recall that in the Miller-Rabin test, we were picking an A uniformly at random from Zn, right?
Yes, yes.
Yeah. So what I'll argue is, since there is a one-to-one map between these sets, picking A uniformly at random from Zn is like picking A1 from Zp uniformly at random and picking A2 from Zq uniformly at random, right?
Okay, okay. Yes.
Right. And then if I want to argue that something happens with something, okay, A satisfies some property with some probability, I can argue that, okay, A1 satisfies some property with some probability, A2 satisfies some property with some probability, and then multiply them because these are independent events, because Zp and Zq are independent.
Yes. Yes, yes,
Yeah, so the entire analysis would reduce to doing analysis over Zp and Zq.
yes.
So over prime modular groups, and which are much nicer.
Yes.
Yeah. Okay, so okay, but we won't use this entire theorem. We'll just use a corollary of it, and that corollary is this. Okay, so Zn is isomorphic to Zp and Zq, right? But now it's not too difficult to show that from here you can argue that Zn cross is isomorphic to Zp. Okay, so what's the difference between these two things? Okay, so over here Zn is a ring, right? It contains all elements from 0 to n minus 1, right? Over here, this is a group.
Yes. So what this ZNX stands for? Yesterday also you used this
Yeah, yeah.
notation.
So Znx is the Zn cross is the set of all A such that so this is a group with with the operation being multiplication modulo n.
Yes.
Yeah, so over here, this is a group, this is a group, this is a group. So what does this direct sum for groups mean? It's the same thing. You take an element from this thing, take an element from this thing, put them in a tuple. How do I define the multiplication operation on them? Multiply two elements of Zp, multiply two elements of Zq, put them in a tuple. Okay. So
Yes.
I can, from the direct sum of Zp and Zq, I can get the direct sum of these two groups, right?
Yes.
Yeah. And so this is a group, this is a group. This structure would also be a group, and this thing is also a group. So over here, the isomorphism is a group isomorphism.
Uh, yes. Yes. But then, okay. Okay. All right. So since we have a single operation here, since this is a group
Right.
isomorphic kind of a thing, so what does it mean to have? Now we won't be representing things as a tuple or
No, no, no. So
just
okay, we will still be representing them as a tuple because of this symbol.
yes.
Okay, so what this says is the following: pick an A in Zn cross. For that, I can come up with U and V, so that U is in Zp cross and V is in Zq cross. Let's say I had B, which was also in Zn cross. Then I can come up with, let's say, UV, W, and X. And A times B mod N. So this is also an element of Zn cross, right? Because of the closure property.
Yes. Yes.
Then what this is saying is this corresponds to UW mod P and Vx mod Q. And
Yes.
these two are also in Zp cross, Zq cross. Again, closure.
Yes, yes, yes.
Yeah, so this is saying, okay, if I have a decomposition for A and B, I can get a decomposition for AB from there. That.
Mm. And is this P and Q unique decomposition of n, or can we have multiple
Okay,
decomposition?
so P and Q are prime factors of N, right? So they have to be unique.
Okay, okay, yes, I
Yeah.
understand.
Okay, so now let's look at fields. Yeah, so we'll reuse this corollary in the proof. So in fact, this is why I had to introduce isomorphism and rings and direct sum, just for this corollary. Yeah.
Yes.
Yes, okay. I can quickly introduce fields. I don't think we'll need them a lot, but fine, yeah, I can introduce them. Okay, so F is set F with two operations. F with the addition operation is a group. So I'll call the additive identity 0 and I'll call the multiplicative identity 1. So F minus 0 with multiplication is also a group. And okay, no, these are abelian groups, yeah. So they're commutative as well. And again, for all A, B, C, and F, A times B plus C is the same as AB plus AC. Yeah, so is this fine? So this is the structure where you have two operations and both induce groups. So for both you need to have inverses. Okay,
Yes.
yeah. And over here I need, okay, so over here I need to remove 0 because 0 won't have a multiplicative inverse, right?
Yes.
Yeah. So example of this is the field of rational numbers, the field of real numbers, the field of complex numbers, then FP, which is the set of 0 to P minus 1. P must be prime over here. It cannot be composite. And addition, multiplication, mod P. Yeah, so like these are some of the canonical examples of fields. So is this fine?
Yes, yes, yeah.
Yeah.
Yes.
So now the thing you were saying, half as in what 2 as an inverse, it has an inverse in Q, right? The set of rational numbers.
Yes. So
Yeah.
Q is the set of the rational numbers.
Yes, Q is a set of rational numbers, R real numbers, C complex numbers.
Yes.
Yeah.
So I have a question here, that is there any specific reason of using the fields? Because I have seen in the course coding theory,
Mm.
where not many error codes, so their algorithm frequently uses the concept of the field. So what is so very special about these fields or the rings people extensively use in the cryptography and in the designing of the error correcting codes?
Okay, so okay, like some of the most basic operations you can do on data are addition and multiplication, right? These are the two most basic uh, algebraic operations, right?
Why not
And
division?
field, yeah, okay, so I'm getting to that. So you have addition, multiplication. Fields are structures where you can do these operations as well as their inverses. So you can also do subtraction, division. So fields are the structures where you can do all four of these basic arithmetic operations, right?
Yes, okay.
So I can do
And
division because division is just multiplication by the inverse, right?
Oh, yes, yes, yes.
Yeah.
Yeah.
Same with subtraction. It's addition by the additive inverse.
Oh, yes.
Yeah.
Yes.
So fields are the structures where you can do these four operations. And the reason you don't just want to use, let's say, rational numbers is because things blow up, right? So we saw in the yesterday's problem solving session that unless you went modulo p, something was blowing up.
Yes. Yes.
Yeah, so that would also happen in, let's say you are trying to construct an error correcting code over rational numbers. You do some matrix multiplication, entries blow up.
Yes. Yes.
Yeah. So like finite fields are used because like the size of the alphabet is fixed. It's small, finite, right?
Yes.
Yeah. Okay, so now we can start with the proof of Miller-Rabin test. Okay, let me do this. I'll copy the algorithm again because I don't want to go back and forth.
So yesterday also I forgot this thing to tell you that is this possible for you that just now you have selected a text and can you change its color to blue? Is this possible in your system?
So text, text, color of what? Which text to blue?
Any
All the
any any
text.
any text you select from your notes and can you change its color? Is this possible?
Yeah, so I can change the color. Yeah.
Okay, so then the thing is that lecture notes of some of the lectures which you have written, so you have used a very light ink, and when I take its print out, so it is not getting
Okay.
printed. So if you can
Okay.
change
So
the notes to
I can change the color for that text, but I'll have to do it for every page. So I
oh,
can't just like select the entire document and change the color.
oh, so when I tried to take the
Yeah.
print out actually, so nothing was getting printed, and it was so
Okay.
light that
So
I could not.
which is this? So this would happen in
In some lectures,
lecture 5-6. I'm using green and oh yeah, lecture 10-11. I'm using orange. So this would happen in those two things. Yeah.
yes, orange is not visible. So
Yeah.
if it is possible for you, then you
Oh,
please
so
take
okay,
the
wait. Is it only orange that's not visible?
orange is not visible and green is also not that clearly visible. So orange and green, two colors. Remaining are visible.
Okay, orange, I should be able to do it just 5 pages. Green is like 9 or 10 pages. So I can do I can do that for orange.
Yes, please
Yeah.
wait for the
Yeah.
thanks.
Yes, I can do it and then upload it again.
Sure,
Upload the
sure.
notes again. Yes.
That would be really.
Yeah. Okay, so this was the Miller-Rabin primality test, and we will do its error analysis. So the first case is that n is prime, and my claim is that in this case, the algorithm always outputs prime. So let's see why. So if n is prime, okay, I'm also assuming n is at least 4, huh? So n is not 2. So n is prime, it cannot be even, right? So the algorithm won't output composite over here, right?
Yes.
Now, regardless of which a I pick, it's in this set n, right? So it's not a multiple of n. And apart from multiples of n, for every element, this GCD is going to be 1, right?
I did not understand this thing. We are randomly, uniformly random. We are picking an element from the set n.
0 to
Uh,
n minus.
yes.
Oh, wait,
And
yeah, this should be 0 to n minus. No, it's fine. Yeah, I can take n over here. I will work with a ring, so it's fine. Yeah, so I'm picking from 1 to n minus 1. And
yes.
so if n is prime, no element in 1 to n minus 1 has a common GCD with n, right? Because
Yes.
otherwise n would have a factor, right?
Right.
So it won't output composite over here.
If n is a prime number, then this
Yeah.
will not output. Yes, right.
Right. So now let's look at the fourth step. A to the n minus 1 is not equals to 1 mod n, then composite, right? So if n is prime, this set 1 to n minus 1 is the group Z cross n, right?
I did not understand this. So why so?
So Z cross n is the set of all elements which are
Yes,
relatively prime to n, right?
yes,
But if n is prime, then everything in 1 to n minus 1 is relatively prime to n.
yes, yes.
So the set from which I'm picking an element randomly is Z cross n. Now Z cross n, if n is prime, okay, so Z cross n is a group with order n minus 1, right? If n is prime.
Yes.
So this is element to its order, which must be 1 by Fermat's last theorem, right?
Yes.
Yeah. So if n is prime, this is going to be 1. So it won't output composite over here either.
Yes.
Right. So now W is the largest number, so that n minus 1 is to the W times T. If it, okay, so I can sort of ignore this. All I need to now prove is it does not output composite over here. Because if it doesn't output composite over here, we know it holds, so it must have either outputted prime over here or prime over here, right?
Right.
Yeah. So let's see why it doesn't output composite over here. Okay, my pencil has low battery. Okay. So why doesn't it output composite in the last step? Okay. So what am I checking? I'm checking that. So, okay, when will it output composite? It will output composite if A to the T to the 2 times R minus 1 is not congruent to minus 1 mod n, right?
Yes.
Okay. But what is R? R is the smallest number, so that A to the T to the 2 to the R is congruent to 1 mod n, right?
Yes.
So, yeah, okay. I need to write. Okay, how much is charged? Okay, yeah, so we'll have to wait for 5 minutes while my pencil charges.
So in the algebra, we do not have any other operation except the four operations, say addition, subtraction, and then multiplication, and then division. So
Yeah,
basically,
so
you do not have any other operation except these two.
okay, so we just have two operations, addition and multiplication, because division and subtraction are their inverses, right?
Yes, yes.
Yeah, so in algebra, you just have two operations.
Mhm.
But everything else you would sort of deal with in things like analysis.
Okay.
Yeah. Okay, so there is square roots, but it's not an operation.
So what
You
about
can
this?
take roots. Yeah.
So what about square root? Is this not an, so the meaning of the square root would be what? To multiply an element with whom?
Okay, so I can define square root like this. The square root of x is the square root of x is any element y, so that y square equals x.
Oh,
That is
I see.
y times y equals x.
Yes,
Yeah, but we don't think of this as an operation.
yes,
At least in algebra, we don't think of this as an operation.
yes. Everything is either a plus or a product in algebra.
Yeah.
Okay. Yes.
Yeah, so the way you would think of square root is the solution of the equation y square minus x equals 0.
Yes.
Yeah. In fact, that's what I'm sort of going to do now. So 23 is good enough. I'll write something, then when I'm talking, I'll again charge it. Okay. So, so when n is prime, uh, easy to see that steps 1, 3, 4 do not output composite. Now the only thing left is composite from step 8, right? So because R is the smallest number such that 8 to the t times 2 to the r is congruent to 1 mod n, comma 8 to the t this and this. Uh, x square is congruent to 1 mod. It t so this is 2 times square, so I multiply by 2. Yeah, this is fine. Okay. So yeah, so I know that a to the t times 2 to the r is congruent to 1 mod n, right? And what's the square of this is the multiplication of this with this, right? So it's a t 2 to the r minus 1 times a t 2 to the r minus 1, which is a 2 t 2 to the r minus 1, but that is a t 2 to the r, right?
Yes, yes. So
Yeah.
how will it help us? How will it help us then?
Okay. That's where the fields come in. So if n is prime, or rather since n is prime, I'm assuming n is prime. These are the only solutions. Okay, so recall that yesterday we discussed that in a field, a degree d polynomial has at most d roots.
Yes.
Yeah. So now I have this degree 2 polynomial x square minus 1 equals 0, right?
Yes. Yes.
Okay, why have I written this twice? Yeah. Okay. So a to the t to the 2r minus 1 and a to the t to the 2r are the only two such elements, right?
Why so? Why so?
Okay, so both of them are solutions of x square minus 1 equals 0, which is a degree 2 polynomial, which has exactly at most two roots in a field.
Because then I can take numbers like say if n is equal to 7, then I can take any number. So basically I'm looking for those numbers. When I take the square of those numbers and take its modulo with the number n, then I should get 1 as a remainder.
Mhm.
So yeah, I remember that there used to be something like, I vaguely remember it used to be some quadratic residues kind of a thing.
Okay.
Concept of the quadratic residues, yes, and quadratic reciprocity law was the other thing. But okay, so yes, so I mean, and why is this so that there would be exact two,
At
uh,
most two.
at most two? Why so? Why
Okay, so
not?
okay, so the proof of the fact that there are at most d roots of a
Yes.
degree d polynomial in a field, that's complicated. So that's not like that's not something simple.
Okay.
Yeah.
Okay.
Yeah. So this will have to take on faith that in a field, a degree d polynomial is at most d roots.
Okay. And on which number are we defining this field? On which set are we defining this field?
Okay, since n is a prime, okay, let me write it like this. This is the field we are working with. So Fn would just be 0 to n minus 1. And I'm picking from 1 to n minus 1, right?
Yes.
And we are
Yes.
doing mod n. So I'm working with the field Fn.
Yes. Yeah.
Yeah. So these are the only two solutions of x square minus 1 equals 0 in Fn, right?
Yes.
Therefore, so now think of 1 and minus 1. Here minus 1 is the additive inverse of 1 in Fn.
Yes.
So it's n minus 1.
Yes. So in between I forgot something. So now I could understand that there would be two roots in the field, say f of n, and why these two roots are a raised to the power t dot 2 raised to the power r and a t dot 2 raised to the power r minus 1.
Okay, so how did we pick r? We picked r to be the smallest number so that this is 1, right?
Which is one.
Yeah,
Yes, this quantity is one,
right.
right?
So if I let me take this as my x. So when I square it, I get 1 squared, right?
Yes.
So this is 1. Square of this is 1. So this satisfies this equation.
Yes.
What about this? So when I take square of this, I would what the square is this, right? Times 2.
Yes.
But this is exactly equals to a to the t to the 2 to the r, which is 1 by the definition of r.
Yes. Yes.
Yeah. So both of these satisfy this, right?
Oh, yes. Yes. Now I
Yeah.
understand.
And okay, so because of this should happen. Because 1 minus 1 also satisfy them. These two also satisfy them, which means 1 minus 1 should be this because these two are distinct, right? So both of these can't be 1. I know this is 1. This has to be minus 1 because I know this is not 1, right? Because of the way I picked r.
Yes.
Because yeah, if this were 1, then r would have been r minus 1.
Yes.
Yeah. So we have that this is 1 and this is minus 1. So this happens and it outputs prime.
Yes.
Yeah. So is it clear that if the number is prime, then output is prime?
Right. Right.
Yeah.
Yes.
Okay. So in case of prime numbers, it doesn't make any errors. It would make errors in the case of composite numbers. Even in case of composite number, it doesn't always make errors. There is only a small set of composite numbers for which it is more likely to make errors than the others. Okay, so in this case, before I proceed, let me define something. Oh wait, I forgot the spelling. CAR. Yeah, it's I think this. Okay, so a Carmichael number is a composite number, so that for every element in the multiplicative group z cross n, a to the n minus 1 is 1 mod n. Okay, this is how they're defined.
Okay. Okay.
Now let's see why these numbers are bad for us. It's because of this step. So if in this step you were to find an a such that this is a to the n minus 1 is congruent to 1 mod n, you would have outputted composite, right?
Yes.
But for Carmichael numbers, you would never find such an a.
Hmm.
Why? Because, okay, so I am picking from 1 to n minus 1, and I'm checking that the GCD is 1, right? So
Yes.
I would only reach this step if these two steps are cleared, right?
Yes. Yes.
So by the time I reach this step, my number is in 1 to n minus 1, and it's relatively prime to n. So by the time I reach this step, I have actually picked a the number that I have is not just uniformly random from 1 to n, it's uniformly random in z cross n,
Hmm. Hmm.
right? Because, okay, what z cross n? Z cross n is, okay, z cross n union the numbers for which GCD is not 1 is 1 to n minus 1, right?
Yes, but then actually I can understand it in light of the Euler's theorem as well, because when we give the proof of the Euler's theorem, say a raised to the power quotient of n is congruent to the 1 modulo n, wherein n
Right.
is any composite number. So many times we see that even for the composite numbers also, I mean the Fermat's theorem hold true. I mean could be true, but I mean for some numbers we may find I mean this thing, but
Yeah,
then
so
they are.
those are exactly the numbers which are called Carmichael numbers.
Oh, I see. I see. Now
Yeah.
I understand. Yes, yes. So, but then in that case, the GCD of a comma n is not equals to 1.
No, no, no. Okay, so over here I'm picking a number uniformly at random from 1 to n. Okay. So now
Yes,
GCD can be 1, GCD cannot be 1, right?
yes,
So over here I know GCD is 1.
yes.
So by the time I reach step 4, I know two things. Number one, the number is from 1 to n minus 1, and number two, the GCD is 1, which
Right.
means I am in Z cross n now.
Yes, yes, yes.
So
Correct.
from here, I would forget 1 to n, I would only focus on Z cross n. So over
Right.
here, A is uniformly at random from Z cross
Understood. Yeah. It's
n,
clear
right?
to me.
And that's why Carmichael numbers bother me, because it, I know now A is uniformly at random from Z cross n. And because it's a Carmichael number, this test will always fail.
Yes, yes.
So there is a chance I might output prime over here or prime over here, right?
Yes.
Yeah. Okay, so first claim is, uh, why is this a block over here? Okay, so my first claim is that if Z is, okay, if the number is not a Carmichael number, then the algo would succeed with probably at least half. So let's see why. If the GCD of A and N is not equals to 1, there is nothing to argue, right? Yeah, because if the GCD is not 1, then in step 3, it would output composite and we are done, right?
Yes.
So okay, I don't need to write one more than it's just Okay, so I can assume that the GCD is 1, and I can assume therefore that yeah, so now I can assume that the number is uniformly random from this group, right?
Yes, yes.
Okay, so now the claim is let H be defined as B such that B to the n minus 1. Yeah, so let H be the set of all numbers so that when I take like when I raise them to n minus 1 and take mod, it's congruent to 1 mod n, right? A is also one such number. So A is in H.
So yes, why so? So we have uniformly picked a number, say A, from this
Oh, okay,
data.
okay, okay. Okay, so okay, okay, what I meant was if this fails, then A is in that set.
If this fails, then A is in this set. Yes,
Yeah,
that
because if this passes, we are good. It outputs composite, we are done.
yes, yes, that is true. That is
So
true.
if this fails, then A would also be in this set, right?
Yes.
Yeah. So what I want to do is I want to say that this set isn't two. If n is not a Carmichael number, then the size of this set is at most half times the size of this. Then since I'm picking A uniformly at random, A would be lying over here, probably at most half, right?
So what is B here is, and what
What
is
is
what
what is what?
what is B here
Oh,
is.
so it's defined like this. So B is any number in Z cross N which satisfies this equation. So
Oh, I
this
see.
is B such that B satisfies this.
Okay. So
Yeah,
then this is the subgroup of this thing, or what? Or which thing are you
that's what
using?
I want to claim. So I will I want to show that this has a small size.
Mhm.
The way I'll do it is I'll first show this is a subgroup.
Okay.
So why is this a subgroup? Okay, so let me pick B1 and B2 in H. Okay, then B1, B2 to the n minus 1 is B1 to the n minus 1 times B2 to the n minus 1, right? But
Yes.
both are individually congruent to one mod n, so their product would also be congruent to one mod n, right?
Right.
So yeah, the closure is satisfied, right?
Yes.
Associative would be satisfied because
Yes.
the operation hasn't changed.
Yes.
Identity would be satisfied because identity of the group is 1 and 1
Yes.
to the n minus 1 is 1 mod n.
Right.
What about inverse? So let's say B is in H. I want to show that B inverse is also in H, right?
Yes.
Yeah, so what is B inverse to the
But then B into B inverse would be congruent to the one modulo n.
right? Yeah, so okay, that's I was I'll prove this.
Okay. Okay.
Yeah, so one way to do it is this. Oh wait, no. Not like this. Okay. Yeah, let me do it like that. Okay. So what is this thing? So this thing is B to the n minus 1 to the minus 1 mod n. I can take the inverse out common, right?
Yes.
Yeah, and I know that this is equal to 1 to the minus 1 mod n. Because b to the n minus 1 is 1 mod n.
Right.
But the multiplicative inverse of 1 is itself 1, right? Yeah, so is this fine?
Yes, yes,
Yeah, so H is a subgroup of Z cross N, right?
yes.
Okay, but then we can use Lagrange's theorem. So what does Lagrange's theorem say? Lagrange's theorem now says that size of H must divide the size of Z cross N.
Right.
Now we know that N is not a Carmichael number, so H cannot be all of Z cross N, right?
So since H is a Carmichael number, then Z.
No.
That.
N is not a Carmichael number.
Mhm.
N is not a Carmichael number, which means there must exist at least one element. Okay, let me write it. Okay, and now size of H divides size of Z cross N. There exists a in, okay, let me call this P. Yeah, so there must exist one such number, right?
Yes, because N is not a Carmichael number, so then
Right.
there exists a number C, such that this thing is.
Because if it, okay, so if this doesn't happen, then for every number a to the n minus 1 is congruent to 1 mod n, but then n is a Carmichael number, right? That's how Carmichael numbers are defined.
Yes, yes, yes.
Yeah. So size of H is strictly less than size of Z cross N. And therefore, size of H is less than equals to half times size of Z cross N. Because the only number that, okay, so no number between half times Z cross N and Z cross N can divide Z cross N, right?
I could not understand this.
Okay, so let okay, so take any number m. My
Mhm.
claim is no number between m over 2 and m can divide m. Why? Because let's say m equals to a times b, right?
Mhm.
B has to be at least 2.
Mhm.
A is not m, so b has to be at least 2, right?
Yes, yes.
So a can be at most m over 2.
Oh, yes, yes,
Yeah.
yes.
So since the size is less, and we know that the size must divide this, it can be at most half.
Yes, yes.
Yeah, so and so A is in H, which is equal to probability A to the n minus 1 is congruent to 1 mod n. This is at most half, right?
Yes.
Yeah, so this shows that if n is not a Carmichael number, then an algorithm is good with probably at least half, and then I can repeat it a few times, I'm done.
Yes,
Yeah, so the issue now is Carmichael numbers, okay?
yes.
Okay, so I'll state a fact about Carmichael numbers. I won't prove that, and we'll use that fact to argue something. That is, n looks like P1 up to Pk, where P1 to Pk are distinct primes. So every Carmichael number is square free. And what do I mean by square free? So a number n is said to be square free if there doesn't exist any other number m, so that m square divides n. Okay.
Yes, I remember there used to be some Mobius function or something similar to that. So there are
Okay.
the Mobius numbers, and these numbers are the numbers which are square free numbers.
Okay.
Yes,
Yes. So
something.
whenever a number is square free, yeah, if I like write down its prime factorization, it would be into distinct primes, right?
Yes,
Yeah, because a square cannot occur over here.
yes,
Yes, okay. And so so we are assuming now that n is a Carmichael number. So n looks like this. And okay, for sake of simplicity, I'll assume that n looks like p times q. But whatever I prove for n equals p times q would also work for like product of k primes almost directly. Okay. So for the sake of simplicity, so now I can use CRT. This is where A is picked uniformly at random from. This is isomorphic to Z cross P direct sum Z cross Q. So this was a corollary to the Chinese remaindering theorem, right?
yes,
Yeah. And okay, so even though I stated Chinese remaindering theorem like this, what is the okay, a more general theorem is this. Let's say n equals P1 times Pk for distinct primes P1 and Pk, then Zn is isomorphic to the direct sum of, okay, let me write it like this. So if n is P1 to Pk for distinct primes, then Zn is isomorphic to Zp1 direct sum with Zpk.
so if in case you are writing something, your screen is not visible to me, and so
Oh,
I don't know the
so is
window
it
you.
visible now?
No, it is appearing completely blank to me. So should I log out and log in again, or is there some issue at your end?
Okay, so I
And
don't know. I am in full screen, so I don't know.
also I log out and I log in again in a minute. So please do
Okay,
that.
yeah.
Yes, it is visible to me now.
Okay, yeah. Okay. So I was saying that we only looked at Chinese remaindering theorem and n was p times q for distinct prime p and q. But like okay, this is just a special case of the Chinese remaindering theorem. The general, a more general statement, even this is not the most general statement, but a more general statement is that if n is a product of k distinct prime numbers, then Zn is isomorphic to Zp direct sum Zpk. And again, from here you can derive a similar corollary. Over here you would also have k many sum. So whatever I'm proving using this corollary for the case when n equals p times q, you can prove using the similar corollary from obtained from here for the case where n equals p1 times p, p2 times up to pk. Okay.
Yes.
So since the proof almost goes through directly, I'll just prove it for the simple case. Okay. Yeah. So now okay, so what does this mean? So A corresponds to, okay, I need one more fact. I think, okay, no, this we discussed yesterday, so I won't write it as a fact. So whenever P is prime, Z cross P is cyclic. Okay. So A, which we picked uniformly at random from Z cross N, I can sort of look at its decomposition, right? But its decomposition would look like G1 to the alpha 1, G2 to the alpha 2, where G1 is a, okay, G1 is a generator of Z cross P, and G2 is a generator Z cross Q. Yeah, so this is where we are using Chinese remaindering theorem in this decomposition. And the reason we are doing this decomposition is now I have a much simple thing to deal with.
Yes.
I have a cyclic group. So
Right.
since A is picked uniformly at random from Z cross N, and there is a one-to-one mapping, that's like picking this element and this element uniformly at random from ZP and ZQ respectively, right?
Yes. Yes.
But I know that every element of Z cross P looks like G1 to the alpha 1. So picking an element like this uniformly at random is the same as picking alpha 1 uniformly at random from 0 to P minus 1, right? Sorry, 0 to P minus 2. Yeah, because the size of the group is P minus 1.
Yes, so it is slightly difficult to digest that it's okay that both are isomorphic according to the CRT.
Right.
The thing is that since you have picked a number uniformly at random,
Mhm.
so as soon as you pick the element A, so then
Right.
G1, G2 gets fixed.
No, okay.
G1 and
G1 and G2 are fixed at the very beginning. They are generators of Z cross P and Z cross Q.
right. So
So
now
once I
yeah,
pick A, what gets fixed is G1 to the alpha 1, G2 to the alpha 2.
right.
So essentially alpha 1 and alpha 2 get fixed. So you can think of this as a correspondence, one-to-one correspondence between A and alpha 1, alpha 2.
Right.
Right. So now what are you doing? You are picking A uniformly at random from some set, right? From Z cross A.
Yes.
But the moment you pick A, alpha 1 and alpha 2 are fixed.
Uh, mm, not alpha 1 and alpha 2 are fixed, but in fact G1 and G2 are also fixed because
So
G1 and
okay,
G2.
G1 and G2 are fixed at the very beginning. They are generators of Z cross P, Z cross Q. They are fixed.
Yeah, yes.
So okay, throughout the analysis, I'll only use one set of generators, right?
Yes.
Since the generator is fixed, to give you an element, I only need to give you the power of the generator, right?
Yes. So alpha 1 and
Big
alpha 2 would vary depending upon the value.
value of A, right? But once I pick the value of A, alpha 1, alpha 2 are fixed.
Yes.
Yeah. But what am I doing? I'm picking A uniformly at random from Z cross N, right?
Yes.
So A has equal probability of being everything from Z cross N, and therefore the tuple alpha 1, alpha 2 has a probability of being every tuple equally likely, right?
Yes.
And when the tuple alpha 1, alpha 2 is equally likely, alpha 1 is equally likely, alpha 2 is equally likely, right? Individually.
Yes.
So picking A1 uniformly at random from Z cross N is the same as picking alpha 1 uniformly at random from 0 to P minus 2 or 1 to P minus 1, whatever you like. Alpha 2 from 0 to Q minus 2 independently. Yeah, because the decomposition of A inside Z cross P has nothing to do with the decomposition of A inside Z cross Q.
Yes.
Yeah. So I have I wanted to prove something for a random A in Z in 0 to p minus 2 and random alpha 2 in 0 to q minus 2. Okay.
Yeah.
Yeah. Okay, so what's the bad probability for us? The bad probability for us was this, right? A to the t is congruent to, this is, okay, so there are two bad probabilities. The first bad probability is this. Yeah, so if I go to the algorithm, I would end up outputting prime if a to the t is congruent to 1 mod n, right? So this is a bad event for me.
Right.
Yeah, but a to the this if and only if g to the alpha 1 t is congruent to 1 mod n and g to the, okay, g1 to the alpha 1 t and g2 to the alpha 2 t is also congruent to 1 mod n. This is where I'm using the isomorphism. So I'm doing some operation on A. I can do the analogous operation on its decomposition because of the
Yes.
isomorphism.
And
Right.
both the conjugations must hold true simultaneously.
Yes. Oh, so sorry. Okay, sir. Yeah. P and Q, not, yeah, because these are the smaller groups, right?
Yes.
Yeah. Okay. So now let P, okay, let P minus 1 be okay, 2 to the W1 T1, Q minus 1 be 2 to the W2 T2, and recall that n minus 1 was 2 to the WT. So this is how we had defined T and W, right? In the algorithm.
Right.
Now, yeah, so G1 to the alpha 1 T is congruent to 1 mod P implies, so G1 is a generator of the group, right? So the order of the G1 must be P minus 1.
Correct.
Otherwise, I would miss out some element.
Yes.
Yes. So order of G1 is P minus 1. But alpha 1 to the t, G1 to the alpha 1 to the t is also congruent to 1 mod n. And G1 to the P1 minus 1 is also congruent to 1 mod n, right?
Why so?
Oh, okay. This I have. And what's the definition of the order? Order is the smallest number such that G to that number is congruent to 1 mod P, right?
Yes.
So P minus 1 is the order of G1. So G1 to the P minus 1 has to be congruent to 1 mod P, right?
Yes.
Yeah. So, and okay, what are the only powers of G1 which are congruent to 1 mod P? The, the multiples of P minus 1, right?
Correct.
Yeah, so P minus 1 must divide alpha 1 T. Because alpha 1 T is one such power, it must be a multiple of P minus 1.
Yes.
Therefore, 2 to the W1 T must divide alpha 1 T, right? Oh, W1 T1, yeah. Because P minus 1, I'm writing P minus 1 as 2 to the W1 T.
Yes.
Yeah. Oh, by the way, this is odd. So W1 and W2 are the largest powers of 2, dividing P minus 1 and Q minus 1. So
Right.
T1 and T2 are odd. Okay. So now over here, T1 is odd, over here T is odd, right?
Yes.
So, okay, this whole thing must divide this thing, but 2 to the W1 cannot divide T, right?
So I understand one thing that T1 should be in an odd number, but why T is an odd number? Okay.
Right?
Yes.
W, right? This was the largest power of 2 dividing n minus 1.
Yes. I
Yeah, yeah.
I now.
Yeah, so over here T is odd. So 2 to the W1 cannot divide T, it must divide alpha 1.
Right.
So 2 to the W1 divides alpha 1, right?
Yes.
Okay. Similarly, 2 to the W2 divides alpha 2. If I were to repeat the same thing for P, sorry, Q, right?
Yes.
Yeah. Okay, so but now what does this tell me? This tells me that my alpha 1, which was uniformly at random from 0 to P minus 2, must satisfy something very strong. That 2 to the W1 must divide alpha 1.
Yes.
So it should come from a much smaller set,
Yes. Yes. Correct.
right? Now W1 is going to be at least 2, at least 1, okay? Why? Because P minus 1 is even, because P is odd,
Yes. Yes.
right? So first of all, these two events are independent because one is happening in Z cross P, another in Z cross Q, two different groups.
Yes.
And I'm picking alpha 1, alpha 2 like uniformly at random and independently, right? So this is the product and this is upper bounded by, okay, this is exactly equals, okay, upper bounded by, yeah. 1 over 2 to the W1 times 1 over 2 to the W2, which is it, wait, yeah, 1 over 4. Okay, so I have this consecutive range 0 to P minus 2, right?
Yes.
And I want a number which is divisible by at least 2 to the W1. So let's say the first number is here. The second
Mhm.
number would appear at a distance of 2 to the W1, again at a distance of 2 to W1 and so on, right?
Yes. Yes.
So if I were to divide this range into chunks of size 2 to the W1, in every chunk, only one number can satisfy this property.
Right.
So there are like a lots of chunk. Okay, so let's say there are k chunks, then the
Mhm.
probability is 1 over k, right?
Yes.
Oh no, wait, not 1 over k. Oh no, wait. So let's say the size of every chunk is k, then the probability is 1 over k, right?
Yes.
At
But in
most. But what's the
but in
size of the chunk? It's 2 to the W1.
yes. Yes. But then
Yeah.
why this value of two is, I mean, W1 plus W2 is equal to 1?
What is 1?
Oh, so because you use this inequality that this thing is less than or equals to 1 by 4, so what does it mean?
Okay, okay. So I have this product, right? What
Mhm.
I'm saying is now W1 has to be at least 1. Why? Because P minus 1 is even.
Yes. Yes.
So this is at least this this is at least one half. This is at least one half. So this has to be a like, oh wait. Sorry, yeah, okay, sorry. This is at most one half because if W1 is larger, this would be smaller than one half, right?
Yes.
Yeah. So this is at most one half. This is at most one. So this is at least, yeah, this is at most half. This is at most half. So this is at most 1 over 4.
Yes.
Yeah. Okay, so this was one bad event.
Mhm.
There is one more bad event, right?
Mhm.
Okay, maybe I think I'm better off using the, I'm just keeping this W1, W2, but yeah, let's not worry about that. I'll worry about that later. Oh, so what's the second bad event? Okay, so the number is composite. I don't want to output prime. So I have handled this bad event, right?
Yes.
Now I want to handle this bad event.
Mhm.
Okay, so yeah. So what's the bad event? A to the 2e times 2 to the r minus 1 is congruent to minus 1 mod n. But again, I would use this that decomposition to imply that g to the, okay, I should write it in the next line. G to G1 to the alpha 1 times t times 2 to the r minus 1 is congruent to 1 mod p, and G2 to the alpha 2 times t times 2. 3 minus 1. Yeah, I'm again using the isomorphism to argue that if I do something for something for A, I can do it for its decomposition as well, right?
Yes.
Yeah. Okay, now what I want to claim is this. No, wait, not this. Okay. Oh, okay, no, I need to impose one more condition. Yeah. Okay, so what's happening is this, right? Okay, so how was R defined? R was defined as the smallest number, so that A to the and so this is how R was defined, right?
Yes.
Yeah. So actually, I need both these conditions. So let me do an and again and copy this. So these two are correspond to the first condition, and these two that I'll write now correspond to the second condition. All I have to do is remove this -1 on both sides. Yes. Okay.
Yes.
Now what I want to claim is this: 2 to the k minus r properly divides alpha 1. Okay, so what does this mean? This notation means that 2 to the k minus r divides alpha 1, but the square of this does not divide alpha 1. Okay, okay, let me write it more explicitly. 2 to the k minus r divides alpha 1. Oh, wait, I don't have, no, what? It's 2 to the, what am I using over here? W1, yeah. So 2 to the W1 time minus R. R is for, it's T1, yeah, okay, this is fine. Divides alpha 1, but 2 to the W1 minus R plus 1 does not divide alpha 1. So this is the largest power of 2 dividing alpha 1.
Yes, but then I could not understand the second congruence wherein the minus one is
Oh,
fine,
so
but
that is coming from this. So over here it's +1, right?
okay.
Yeah,
Yes.
yeah. Okay, so what is happening is this thing, okay, for this element, G1 to the alpha 1 times T, 2 to the R is the first power, so that that element to the 2 to the R is congruent to 1 mod P, right?
Yes.
Yeah, and for a smaller element, that's not happening, which means the smaller element is -1, this element is 1. Yeah. Okay, so what I know is this, right? P minus 1 divides alpha 1 times T times 2 to the R, because P minus 1 is the order of G1. Therefore, 2 to the K, why am I writing K? 2 to the W1 times T1 divides alpha 1 times T times 2 to the R. But again, T is odd, right? Therefore, 2 to the W1 must divide alpha 1 times 2 to the R, and therefore 2 to the W1 minus R divides alpha 1. Okay.
Right.
But now suppose that this also divided alpha 1, right?
Mhm.
If 2 to the W1 minus R plus 1 divided alpha 1. Then 2 to the W1 would divide alpha 1 times 2 to the R minus 1. Just taking the R minus 1 on the other side.
Yes, yes.
Yeah. And therefore, 2 to the W1 would divide, okay, 2 to the W1 T1 would divide alpha 1 times 2 to the R minus 1 times T, right?
Yes.
Because over here, this divide, over here, this divides, okay, this divides alpha 1 times 2 to the R and T1 divides T. Therefore, P minus 1 divides alpha 1 times T times 2 to the R minus 1. But P minus 1 is the order of G1. So if P minus 1 divides a number on the right side, then G1 to that number must be 1, right?
Right.
But what are we observing? It's minus 1.
Correct. Correct.
So this must divide, this must not divide, and so this properly divides.
Right. Right.
I.e., this is the largest power of 2 that divides alpha 1.
Yes.
And it's the same thing for like 2 to
But
the, yes. Yeah. Okay, so now for any R1 in, okay, so by the way, what's the range of R1? Okay, sorry, what's the range of R? There is just R over here. So let me go to the definition of R. Okay, so R was something, okay, R was at most W, right? Because, okay, let me go to the very algorithm. Yeah. So I know that N minus 1 is 2 to the W times T. And I know that A to the N minus 1 is going to be 1, right? So this R goes at most till W. It goes from 0 to W, right? Yeah,
Right.
so R is at most W. In fact, over here, from this to I can say something much better. So sorry, from this to I can say something much better. R is less than or equals to the minimum of these two. Yeah, because otherwise this would become 1 over 2. This would also become 1 over 2 or something like that, right?
Yes.
Yeah, otherwise this subtraction won't make sense. Because yeah, once you go to real numbers, everything divides everything else.
Right.
Yeah. So R is at most W1, W2. Okay. And W1, W2. So these are at most why? Because P minus 1 was 2 to the W1 times T. So if W1 was more than log P, this can't happen, right?
Yes.
Yeah. So R goes over a much smaller range, so I can use union bound over R. So what I'm going to do is, okay, there probability there exists an R in this range. Okay, let me say that this minimum is just log P. I'm assuming P is smaller than Q. 0 to log P. So R in 0 to log P such that 2 to the W1 minus R divides alpha 1, but 2 to the W1 minus R plus 1 yeah, does not divide alpha 1. So I can use union bound, right? So I can use union bound to upper bound this probability, right?
Yes. Yes.
Yeah. Okay, now what is this probability? So this is upper bounded by, okay, so this should exactly divide. Okay, for a fixed R, yes. So this should happen for a fixed R, right? So over here, R is fixed. Since I'm summing over R is fixed.
Mhm.
The only randomness is coming from the randomness of alpha 1.
Mhm.
Okay, now for any alpha 1, there is going to be exactly one largest power which divides, right?
Yes.
And I must end up picking that power.
Right.
So W1 minus R should be that power. And so R must be something that it's that power. Sorry, it's W1 minus that power, right?
W1 minus that power. Yes.
Basically, R must be a very fixed value.
Mhm. Mhm.
So now all I need to do is find out what's the range of that value. So
Mhm.
what's the range of the largest power dividing alpha 1? What was alpha 1? Again, what's the largest value of alpha 1? The largest value of alpha 1 is p minus 1, right?
Yes.
And the only possibilities are, uh, okay, no, I can do something better. Where did p minus 1 go? Okay, it's here. So this is what p minus 1 looks like. So if I wanted to divide exactly, I'll have to divide. Okay, it cannot be more that power, that the largest power that divide alpha 1 cannot be more than W1, right?
Yes.
Yeah. And I want my R to be such that this is exactly that power. Okay. So I can upper bound this by 1 over 2 to that thing minus R plus 1. That's it. Did I get this right? Um, yeah, so my range is this. Wait, no, it's a mistake. Okay. So my range is up to alpha minus 1. Okay, now I want to divide this. Okay, so I have this number. My range is up to alpha minus 1 and okay, my range is slightly larger. Wait. Hmm. Okay, yes, yeah. So the power can be at most W1. So I have how many possibilities? I have possibilities from 0 all the way to W1, right? So it's W1 plus 1 possibilities.
W1 plus 1 possibilities for what?
Okay. For the power that, okay, so what do I, power that, okay, the power of 2, the largest power of 2 dividing alpha 1 is fixed, right?
Yes. Yes.
Once
That
I
is
fix alpha 1.
yes.
But how many, and that number should be equal to this. That's what I want,
Okay. Okay.
right? For a fixed R. But
Mhm.
how many such values of, okay, so what are the possible values for that power of alpha 1? Sorry, that power of 2. It can be 0, it can be 1, it can be 2, it can be all the way up to it can be all the way up to W, right?
Right.
So it's W plus 1.
Mhm.
So those are your options, right?
Mhm.
And from that you subtract R, not from W1, because you have this extra 0.
Yes.
Yeah. So this is for 1 R. Again, I can sum for all R. Okay, I shouldn't have summed over here. Okay. Okay, so the final property that I'm interested in is this, right? This thing and something else. So this was for P. I also need to do the same thing for Q, right? And that's the property I want to upper bound. This should become alpha 2, 2. So this is a property I want to upper bound. I can do a union bound, but now everything would have two components, right? For one for this, one for this. So for P it was this. So this would be upper bounded by R 1 over 2 to the W1 plus 1 minus R times 1 over 2 to the W2 plus 1 minus R. This is for P, this is for Q. Is this fine?
Yes. Yes.
Yeah. Okay, so okay, now okay, this sum is bad. I just want to say that this is upper bounded by 1 over 4 and I am happy. But yeah, this sum is bad. Okay, so let me do this sum. 1 over 2 to the W1 plus W2 plus 2 is fixed times sum over R in 1 to log P. I'm assuming log P is the smaller one. 1 over 2, 1 over 4 to the R. So it's this sum, right?
Yes, so we brought this entire thing W1 plus W2 plus 2 outside the summation, and we are left with what? 1 divided by 2 raised to the power minus 2R.
Oh yeah, okay, wait. So this is 4 to the R, right?
Yes.
Yeah.
Yes.
And okay, so now this is a GP, so this is easier for me. Okay, let me not use the log P upper bound over here. Let me use this W1 upper bound over here. So yeah, this was R was at most the minimum of W1, W2, right? I'm assuming
Yes.
W1 is the smaller one, so let me use that upper bound over here because then I need to add it with the bad probability 1. It will make it much simpler if I use that. In 1 to W1. So this is like 4 to the W1 plus 1 minus 1 over 3. Right.
कौन से GP kind of thing है?
Yeah, this is a GP.
Yes. Yes.
Yeah. Yeah. Fine. Yes. Okay. And okay, so this is bad probability 1. So bad probability. So this is bad probability 2. So bad probability 1. So what was bad probability 1? I shouldn't have upper bounded it by 1 over 4. That was bad. That was a bad idea. Okay, I'll use this upper bound.
Right.
Yeah, 1 over 2 to the W1 plus W2 times 1 plus 1 over 4 to the W1 plus 1 minus 1 over 3. Oh, wait, no. Do I want to ignore this 1/4? Would it? Yeah, that would make my life easier. Okay, so the sum of two bad properties is this. Yeah.
So can't we ignore? Can't we take the lowest values of W1 and W2 is equal to 1 here?
Yeah, we can do that, but okay, so I can do that over here, but I can't do that over here, right? So I want to upper bound this. I need to take the lowest values over here and the largest value over here.
Oh, I see. Yes.
That's okay. You might be able to take the lowest value at both places, but in that case, you need to prove that the maxima is achieved when both take the lowest value. And for that, you need to take derivatives. I don't want to do that.
Oh, yes.
Yeah. So what I'll do is, okay. So the bad property is this. Now, if I ignore this 1/4, the property only becomes larger, right?
Yes.
So I'll ignore it and say this is 1/2 to the W1 plus W2 times. So 3, so this is 4 to the W1 plus 1 plus 2 over 3. Did I get this right?
This is not right, I guess. 3, because this thing will come as what? 12. So we have ignored 1 by 4 here. So this will come as 3 plus 1, 2. So plus 2. This is right. This is right.
Yeah. Yes. And okay, wait. No, wait, there is some issue somewhere. No. So I put. Oh, okay, okay. W1 was the smaller one. So this is 4. No, no, no. Okay, this one should not appear over here. Did I make a mistake? Okay, I should not be ignoring the 4. Yeah, I should not be ignoring the 4. Okay, so this is, I think, okay, maybe, okay, let me do this, see if this works. W1 plus W2. And so this is 4 to the W1 plus 3 over 3. Does this work? 1. No, even this doesn't work. Wait. Minus 1/4. So this is something smaller. Okay, this is 1. This is okay. Yeah, this should be something strictly less than 3. So what's 3 minus 1/4? It's yeah, this should work. Okay, so I'm not ignoring this 1/4. So this is minus 1/4, and when I add 3 to it, I get 2.75.
Yes.
Okay, so now I know. Okay, I assume that W1 was a smaller one. That's why I'm getting W1 over here. And I know that W1 and W2 both are at least, okay, W1 and W2 are both are at least 1, right?
Yes.
So in the worst case, this is 1/4. This is 4 plus 2 point, okay, so this is 12 and this is 4 plus 2.75.
Right.
Okay, first of all, as W1 increases, this only gets better for me, right? This ratio only gets better for me. Why? Because this is at least because W2 is at least W1, right?
Yes.
Yeah. So as W1 becomes larger, I can sort of ignore this 2.75, right?
Yes, that we can always ignore. Yeah.
Yeah. So this to cancel out, and I'm left with 1/3. So as
Yes.
W1 becomes larger, it's good for me. So the worst case is when for the smallest value of W1.
Yes. Yes.
So now we can use the smallest value of W1 because we have argued that's where the maxima would occur.
Yes.
Yeah. So when I use the largest value of W1, sorry, the smallest value of W1, that's 1, right?
Right.
Because P minus 1 was E1. So this is 1/4. So this is 1/4. This is 4 plus 2.75, and this is 3. So it's 12 versus 6.75. So this is not less than half, but okay, this is okay.
1/3.
No. Okay, it's not less than half, so it can't be less than 1/3, right? It's less than 2/3.
Okay.
So this is 6.75, and 6.75 is less than 8. So this is less than 8/12. 8/12 is 2/3.
Mhm, mhm,
Yeah. So the probability, the sum of two bad probabilities is at most 2/3.
mhm.
And now I can repeat, right?
Yes.
Yeah. So this finishes the error analysis for uh, like Miller-Rabin test, and we are already half an hour over time.
Yes.
Yeah.
Yes.
So do you have any questions for like this or anything in the entire course?
No, I understood the gist of, I mean, this
Yeah.
proof. I need to refer it multiple times to
Mm,
understand precisely.
yeah.
Uh, yes, I mean, by and large, I have understood the different concepts you deliver in this course,
Right.
and especially that pattern, that how to, I mean, proceed with the problem using the randomized algorithm. That polynomial thing, that we convert the thing
Yes.
to the
Yes.
polynomial
Yeah.
with a lesser degree, and then we can go for the PIT thing.
Yeah.
Yeah, so I understood most of the concepts, and you really
Thanks.
need a tremendous efforts right, to make me
Yeah.
understand these concepts.
Thanks.
Yeah, almost 25 hours course, and this is equivalent to half a semester, or so yeah, half
Oh,
a
yeah.
semester course, certainly. Yeah, thank you so very much
Yeah.
for offering this course. And, whenever you
Okay.
offer, yeah, any other course in the future on IEEE, then please do.
Okay. About that. So I hope I don't have to offer any other course because I hope to graduate by the end of this semester.
Congratulations, congratulations. You
Yeah.
can do.
I hope to. Hope is doing the heavy lifting over here.
Yeah,
Yeah. Okay.
good.
Yeah. So then see you. Bye. So I'll upload these notes and so I'll upload this note, the notes for these 2 days problem solving session, as well as all the 3 videos on the course page.
Yes,
Yeah.
that would be great.
Yes.
And if you can suggest some resources for the beginners and who want to pursue their, I mean, research work in the theoretical computer science, then are there resources available, or I mean, or any roadmap which they can follow if they want to continue doing research in the theoretical computer science? Because most of the people nowadays go for the machine learning or the deep learning stuff.
Mm. Yeah. Okay, so like it sort of depends on which area in theory are you interested in. For example, if you're interested in algorithms or complexity theory, then the usual roadmap would be, and let's say a graduate algorithms course, a complexity theory course, a randomized algorithm or approximation algorithms course. So this would sort of be the roadmap. If you are
Okay.
interested in, let's say, cryptography, then your roadmap would be a bit of algebra and then cryptography courses. If you're interested in, let's say, logic, then your roadmap would, I think, just be logic, some like advanced law courses in theory of computation. In graph theory, it's essentially advanced graph theory courses. So it depends on the sort of which sub area you are interested in.
Okay, and then how to pick a problem, a research problem, and wherein the
Oh,
person
I
what
wish I
to.
knew the answer to that. Like, yeah. So yeah, okay. So okay. Let me stop the recording and then I can tell you more about this.
Yes, yes, yes.
Yeah. So is the recording stopped? Okay, the recording has stopped. Yeah. So far what has